Alright, let's talk about something that makes your PC feel snappy. Something that works its magic every single second you're gaming, editing, or just browsing memes. I'm talking about cache memory. Think of your computer's main memory, the RAM, like a massive warehouse full of all the data and instructions your computer might need. It's huge, but it's also kinda slow to get things from. Your CPU, the brain of the operation, is incredibly fast. It's like a hyper-caffeinated worker who needs tools and materials right now. If it has to wait for data to travel all the way from the RAM warehouse, it just sits there, twiddling its digital thumbs. That's a huge bottleneck. This is where cache memory swoops in to save the day. Cache is a very small but ridiculously fast chunk of memory located right on or next to the CPU. It's like a tiny personal workbench right next to our super-fast worker. Instead of making the long trip to the warehouse for every single tool, the CPU first checks its workbench. If the data it needs is already there, bingo! It can grab it almost instantly and get back to work. This simple idea is the foundation of modern computing performance. Without cache, even the most powerful CPUs would feel sluggish, constantly waiting for data from the slower main memory. It's the unsung hero of speed. So, how does the cache know what to store on its tiny high-speed workbench? It doesn't have a crystal ball. Instead, it relies on a brilliant principle called the locality of reference. This just means that programs have predictable patterns. There are two main types of locality that cache cleverly exploits. The first is temporal locality. The temporal part refers to time. If the CPU accesses data now, it's likely to need that exact same data again soon. Think about a loop in a program, or a variable that's used multiple times in a function. Cache keeps that data handy after the first use. The second type is spatial locality. The spatial part refers to space or location. If the CPU accesses one address, it's likely to need nearby addresses soon. Data and instructions for a task are usually stored together in memory, in a neat row. It's like reading a book. Once you read one word, you're almost certainly going to read the next word. You don't just jump to random pages. The cache takes advantage of this by not just fetching the one piece of data the CPU asked for, but a whole chunk of adjacent data along with it. This is where the idea of cache blocks or cache lines comes in. Your computer's main memory is divided into these fixed-size chunks, say 64 bytes each. When the CPU requests a single byte of data that isn't in the cache, a cache miss. The cache doesn't just go to RAM and grab that one byte. That would be wildly inefficient. Instead, it fetches the entire block, or line, that contains the requested byte and stores it. Now, thanks to spatial locality, when the CPU inevitably asks for the next piece of data, which is likely in that same block, it's already in the cache. Okay, so we're pulling entire blocks of data into this tiny exclusive cache. But wait, the cache is small and the main memory is huge. How does the cache decide where to put the data it pulls from RAM? More importantly, what does it kick out when it runs out of space? This is where mapping and replacement policies come into play. Mapping is the set of rules that determines where a block from main memory can be placed inside the cache. The simplest method is called direct mapping. In this scheme, each block from RAM has exactly one specific spot in the cache where it can go. It's like having assigned seating at a concert. Your ticket for seat A1 only works for that one seat. This direct mapping approach is fast and simple to implement, but it has a downside. What if your program needs to frequently access two different memory blocks that happen to map to the same spot in the cache? The cache will be forced to constantly kick one block out to make room for the other, and then immediately kick that one out to bring the first one back. This is called thrashing, and it's super inefficient. To solve this, we have fully associative mapping. In this method, a block from main memory can be placed in any available spot in the cache. It's like open seating. You can take any empty chair you find. This is very flexible but requires complex hardware to search the entire cache. The perfect compromise between these two extremes is set associative mapping, which is what most modern CPUs use. This method divides the cache into several sets or groups of cache lines. A memory block from RAM is first mapped to a specific set, but within that set, it can be placed in any of the available lines. It's like your concert ticket assigns you to a specific row, the set, but you can choose any open seat within that row. This gives you a good dose of flexibility to avoid the thrashing problem of direct mapping, without the crazy hardware complexity and cost of a fully associative cache. It's the best of both worlds. But no matter the mapping, the cache will eventually fill up. When a new block needs to be brought in and there's no empty space, the cache has to decide which existing block to evict. This is handled by a replacement algorithm. A common one is least recently used, or LRU. This policy does exactly what it sounds like. It kicks out the block that hasn't been accessed for the longest time. The logic is that if it hasn't been used in a while, it's probably not going to be needed again soon. This is a direct application of temporal locality. By intelligently choosing what to discard, the cache maximizes its chances of holding on to the most useful data. So, how do we measure how well the cache is doing its job? The two most important metrics are the hit rate and the miss penalty. The hit rate is the percentage of time the CPU finds the data it's looking for in the cache. A high hit rate is what you want. If your cache has a 95% hit rate, it means that 95 out of 100 times, the CPU gets its data almost instantly. The other 5% of the time, it results in a cache miss, forcing the CPU to wait for the data to be fetched from the much slower main memory. The delay caused by a miss is known as the miss penalty, and it can be significant, stalling the CPU for hundreds of cycles. To keep that hit rate high and the miss penalty low, system designers use some clever tricks. One of them is writing data back to memory. When the CPU writes new data, where does it go? With a write-through policy, the data is written to both the cache and the main memory at the same time. This is simple and keeps everything in sync, but it can be slow because every write has to wait for the slow main memory. The alternative is a write-back policy. Here, the CPU only writes the data to the cache. The cached line is marked as dirty, and the data is only written back to main memory later, usually when the line is about to be evicted. This is much faster for frequent writes. Another technique to speed up data access, especially during a cache miss, is memory interleaving. Instead of treating main memory as one big monolithic block, it's organized into multiple independent banks. Think of it like having multiple checkout lanes at a supermarket instead of just one. The system can start fetching a chunk of data from one bank, and while that's in progress, it can immediately start the next fetch from a different bank without waiting. This parallel access allows a continuous stream of data to be sent to the cache, effectively hiding some of the latency and reducing that painful miss penalty. It helps fill the cache faster, getting the CPU back to work sooner. Ultimately, all these components, locality, mapping, replacement policies, and write strategies, work together in a beautifully complex dance to make your computer feel fast. A good cache system with a high hit rate ensures the CPU is constantly fed with the data it needs, allowing it to work at its full potential. It's why upgrading from an old CPU to a new one with a larger, smarter cache can feel like a night and day difference. Every click, every frame rendered, and every application launched feels more responsive because the cache is working tirelessly behind the scenes, making sure the right data is in the right place at the right time.